Hey guys, how's it going? Welcome to another episode of Ferris Makes Hardware. I'm particularly proud today because as of last night, I can officially get VGA, or actually HDMI output from the xenowing. So this is actual output from the xenowing right now. I have this capture card that I've used previously for capturing composite signals. I don't know if I've ever actually shown that on the stream before. Well, here it is. So this is capturing output from the xenowing. The xenowing is running a very simple program where it starts by plotting a pixel in the center of the screen and sort of moving around the plot position in X and Y. And whenever it hits one of these walls, it just bounces back. And the color is determined. So this, I'm using 16-bit color is what I've decided for the xenowing. And it just starts with a color that I think is 0 or something, and then just adds 1 to it, I think, when it starts. And so then as it kind of scans through the screen, this is just the interpretation of that 565 bit pattern that you get when you just add 1 every time. So yeah, pretty exciting. In fact, I can restart this. So here we have the console output from the xenowing. I can hold reset here, let it go. There we go. So what it prints is it says that it's online, and then these are actually some debug prints of some of the registers in the HDMI transmitter. The HDMI transmitter that I have on the board here is an ADV7513, which is a fairly standard chip for this stuff, I guess. I had actually gotten it to work before with this big ugly state machine and everything when I just first got the FPGA, and it took me a few weeks, I think, to actually get this working. Also, I just noticed this actually had a bug in the output here. That's the first I've seen actually where this goes wrong, which is pretty cool, I guess. That's funny. Anyway, with this particular chip, there's an I2C bus, and that's what this is actually doing, is it's reading these different registers from that I2C bus. And for the most part, these are just going to be, I think these are just a bunch of registers that you don't actually have to set up because they're reset when you turn the chip on. So, man, there's a lot that I went through in the last week. I think I had talked about hooking up this I2C bus, and what I ended up doing, if I pull up the memory map, is pull this up and I'll move the xenowing output a bit. Then we'll talk more about how that works. Pretty proud about it, to be honest. Just let that keep running. So let's see. So I also went through, and I don't remember if I did this on stream, but I actually removed, like I used to have listed all the mirrors for the ranges where all these things were, like a given address range. This program run would actually be repeated for all these bits as well up until this range. And I actually removed all that from the docs because I decided that I want all of that to be undefined outside of any of these ranges. Because if I ever want to change the implementation, if there's an easier way to do this mapping and read the bits differently or something, I want to maintain that freedom without having to worry about if I'm supporting this. And like no one's using this anyway, so it doesn't really matter whether or not I support that. But another way to look at it is I don't have to make changes to this document as much if I make changes to that stuff. So that seemed like a good idea. So I removed all that, and then I added down here a couple things. So I mapped this range to the display interface. And this first register is a read register for the I2C input, and then the bottom 2 bits, looks like I have bit 0 is the clock, and bit 1 is data. And this is just raw from the I2C bus. In fact, the way I mapped this up, well, I'll get to that in a second. So this first word here is just that. And then you can write to it with this register. And actually the way I implemented this is, again, another example of this, is I actually just implemented both of these as the same register. So if you were to read from this or write to this, you actually get the same result. But what I say up here is that bits other than these are undefined, and also reads and writes to, no, wait, what is it? Yeah, reads from regs not marked R, writes to regs marked W, have undefined behavior, all that kind of stuff. So that's a valid implementation. And it just made it a little simpler. And then I also added this register here, which is a frame buffer base address, so I can actually change where that is in the xenowing's memory. So for example, I just thought of a good way to show this. I'll pull up main.c, and I'll take my frame buffer here, and here it says display set frame buffer adder. I'm going to do this, frame buffer plus frame buffer height over 2 times frame buffer width. And this should mean that the address that we give the display hardware is halfway through the buffer, so we should see like the top half disappear. So now if I go and I rebuild my ROM and everything, assuming everything works properly, then as soon as I make this, we should see, if I do make, this will reload. And we'll see, yeah, we got a bunch of garbage. That's actually awesome because I hadn't run this before. And this is just uninitialized memory, which is great. So that's exactly what we wanted to see. So the reason why I mapped that as an address is because it just makes sense to me to be able to point that anywhere, because it doesn't really matter in terms of, like, the implementation doesn't care where that is. It's all the same memory in terms of the actual hardware that's on the board. And as you can see on the top at the code here, I have the width and the height. 320 by 240 is the resolution I chose, and I'll talk about why that is, because originally I was going to go for 640 by 480, but I did some math and decided that was a really bad idea. And then this is where the frame buffer is defined. I just allocate some memory statically. This is a global variable. And I make sure this is aligned on an 8-byte boundary. And the reason I do that is because the memory interface that I have is 64 bits wide. And if I align the frame buffer on that kind of address, then I can read 4 pixels, 4 pixels at a time out of that, which is really nice. Yeah, always a bad idea to do some math. In this case, it was a really good idea. I think I saved a lot of time by by doing that math. By the way, howdy guys in the chat. Yana Moran, Garrett Kelly, Dark Second, Chief Detector, Repnap, Alkama. Good to see all you guys. By the way, thanks again, Garrett Kelly and Dark Second, and Alkama, and Repnop for the subs. Wow. That's awesome, you guys. Anyway, so aligning this on that 64-bit boundary just means that I can pull entire words out and get 4 pixels at a time, and that ends up being really helpful. Quirk Shooter, what's up? Disused, how's it going? This is my xenowing. This is actually displaying pixels out of memory now. This is, I'm actually really excited. I did so much to get this to work. Hey, Daniel Cullen. Congrats on the new gig, by the way, whatever that is. But yeah, this is from a capture card I have that's capturing HDMI that comes straight out of my xenowing console right now. This is just a bunch of system memory. It's shared memory, this particular architecture. So I'm gonna put the frame buffer back, by the way. But yeah, the reason I also made this settable is that this is the way we're going to implement double buffering. We're just going to, in the code here, change whichever frame buffer we display every frame. So that should work out really well. And I'll build this again so we fix the output. So that proved that it worked. I hadn't actually tested that. I just figured it worked because otherwise this would have been all messed up. In fact, if we remove this call, we probably get something misaligned or something, or maybe this ends up being at the same point in memory. No, we can see at the top here. It looks like it's actually a bunch of stale stuff, which is fun. I bet if we reset, maybe that changes or not. Let's do a hard reset. Oh yeah, that's a different ROM, so we need to load it again. I think this is fun, by the way. Yeah, it probably just didn't allocate a frame buffer since we never set this. Or put it somewhere else, who knows. Maybe it optimized all the code using it away. And we're just getting the stuff left over. Anyway, I think it's fun. Yeah, disused. I got C running. It's, I don't support everything currently, especially, I think I did something where I tried to clear the frame buffer and it ended up the compiler generated a call to what's the call? Why can't I remember this? Memset? And I don't have any support for that yet, so I just kind of ignored it for now. Oh, that's awesome, Dark Second. That game is amazing. But yeah, so there's a lot of stuff that I ended up doing. I talked a bit about how I mapped this frame buffer address and then how I mapped the I2C. So I mapped the I2C directly to these bits in this register. And that was purely a workflow decision. I decided I would just do that and then just bit bang the I2C interface because it's not a particularly difficult protocol to do that with. And what was nice about it is that because I did it in software, I could iterate on it really fast against the real hardware. So hooking this up is basically trivial. And I do actually want to show in the RTL viewer how I hooked that up because there's some useful stuff here. Chief Detector says, "Are you using your own libc?" No, I don't have any of that support yet. So that's the right now. I haven't generated any code that calls into libc or would need libc. So far I've just avoided the issue. I'm guessing though, as long as I have a libc that's built for RV32i, it'll just work. But I need to probably just put in the right compiler flags to make that happen. Anyway, this is the xenowing here. What I did is I have in the xenowing module itself, if we zoom in here, so I don't want a lot of bidirectional signals coming in and out of the xenowing itself, and that's for simulation. Makes it a little easier if we don't have those kind of signals. So what I do is I think I've separated the I2C clock and data as separate in and out signals. And then in this top level stuff, where I actually hook it up to the hardware, I put these tri-state buses on it because I2C is a open collector bus with 2 wires. And so what happens is that there's pull-up resistors on the bus lines that normally pull those high if there's nothing actually driving them. And then what you do is if you want to control them, you pull them low. And the reason they do this is so that if there's some kind of mishap or something, you don't have one end of you don't have, for example, the master, which in this case is the xenowing driving it high, and then the slave, which is in this case the transmitter, driving it low, which would give you a short from VCC to ground. We don't want that. So similar to the Virtual Boy, the communication port, if you guys remember those streams from like a year and a half ago, these are just open collector. So I do that kind of mapping out here, but then what the xenowing sees is separate inputs and outputs, even though the inputs are going to be the same as the outputs if we actually drive them low. Otherwise, they're going to be high because of the external ones. Now, in simulation, I don't actually have any code that simulates this stuff yet, so I need to fix that at some point. I need to figure out what I want to do with that. But anyway, that's just sort of how that's mapped. So then, again, the software sees a couple bits that it can read to see what the status are of these 2 bits, and then it can also write a couple bits that will either pull these low or leave them disconnected, in which case they'll be pulled high by the external pull-ups. And again, this was really nice workflow-wise because then I could just go in. So I also did a bunch of refactoring here so that like all the software is kind of split up into different modules now. I have xw.h, which is all the xenowing stuff. And then I have things like cpu.h or display.h, which is where the most relevant stuff here is. And so if I go to display.c, I have a lot of stuff in here. So these are the 2 registers defined here and the frame buffer address register. Same stuff as in the memory map. It's just this how it looks in the code. Then these are the clock and data bits, and then I have some defines that just help me set or clear them. And then I also have some stuff about the particular device that I'm driving. So its I2C address is 7.2, read bit, write bit. And then we have some registers within that as well, which is there's a power down register that we have to enable. So first we query the monitor sense to make sure there's a monitor there. And if we detect one, then we can disable power down. And that will actually bring the chip into power up. So actually we can look at the actual things to do this. So this display init right now, it calls this ADV thing. I have a bunch of to-dos that I need to clean up, but so far it just calls the init for this particular transmitter. And that waits a bunch of time so that the chip can power up, it's defined in the datasheet that you need to do this. That should be a 2, not a 3. No, this should be a 3 because we're at 150 megahertz. So this actually does work out. And then we wait for, again, this monitor sense to be high, which means there's a monitor connected. When we detect that, we can disable power down, and then you're just the data sheet tells you to write these registers. And if I pull up the data sheets, actually, because I think I have this is the data sheet for the chip itself. And this mostly just talks about the characteristics of the chip. There's some high-level block diagrams of it in this thing, I think. Maybe that's in the other docs. But I think it's the Programmer's Guide, ADV 7513 Programming Guide, it's called. And these you can just find online. And the nice thing here, yeah, this is not a data sheet in that sense because it's actually quite good. So right at the beginning here, if you look at the table of contents, there's stuff about the chip and how you read and write registers. And the quick start guide is really helpful because it tells you exactly what you need to do. So you do this to power it up. You need to set these fixed registers, and it doesn't go into anything about what these do. They just need to be fixed. I'm guessing this is like some extra internal configuration that you're not supposed to mess with, but they probably put it into the chip just in case, and then found out that these were optimal settings, or at least these were intended settings. And then all the stuff about input mode, you don't actually have to set. At least doesn't seem like you have to, because these will be reset when you bring the chip out of power down. So that's it. We just do that. Hey, G Superland, good to see you again. And then I also do a debug read of a bunch of these registers, but I actually don't need to do that, so I'm going to comment that out. In fact, I'll actually just get rid of it because it's in Git history anyway. So you don't really need to do any of this. This is not wrong. And then, yeah, this chip can also transmit audio, and I would love to do that at some point. So I might end up splitting this in the code between stuff that inits this particular chip, which is distinct from initializing display specifically and audio specifically. No worries, G Superland. So yeah, so this is really straightforward, this init procedure. And so you can see I use these I2C get and I2C set functions here, which I've defined right above this. I also have these debug read and get digit stuff, which we'll just put them out over the UART. And if I just delete that code, I might as well just delete this code. I'm just going to get rid of it because, again, it's in Git. So yeah, this is I2C set and I2C get, and these are just like these are functions that bit bang individual parts of the protocol. So for set, we do something called a start condition, and then we're gonna write a few bytes, and then we do a stop condition, and that will do an entire register write. So we do that, and the first byte we write is the address of the device, including a bit that says we're gonna write to it. Then we write the index of the register, and then we write the address of the register, and then we write the actual value. So that's a write, and then a read is a start condition. We write the device address followed by a write bit, and then we write the register address. Then we send another start condition without doing a stop, and then we address the device again and say we're going to read. So like this first part is actually the same in both cases. And then we actually read a byte, which is almost the same as writing a byte, but we let the other side actually drive the data line, pull in all the bits, and then we stop. And there's this true or false thing here because you can acknowledge, if you acknowledge the read, then it will actually continue to read registers. And I actually made that mistake and got the same register value over and over again, which told me that I got timing, but not the other parts of the protocol right. So that's kind of a gotcha that you need to not acknowledge the data it gives you so that it can actually stop sending you data. And then you can not just sit there and hang while it holds your data line low. So that's kind of funny, but yeah, so relatively basic. And then these individual pieces are just like, here I have a read bit and a write bit function. And then these are read bit just actually drives the lines and then has some delays. And I made this I2C delay because like most of the time, in fact, I think I ended up with all the time I end up just delaying one now that I see this, because there was a time where I had a couple twos here. It's a good thing I'm going through this because I'm just going to go ahead and clean a bunch of this up while we're doing this. Just delete this parameter. And then instead of having this ticks count here, then we're just going to do this. Easy. And we drive this we implement this so that we get 400 kilohertz bit rate with this. So each tick here is a quarter of that, and so 4 of those will is what we need to do all the different transitions to do one clock pulse. I mean, that's it. Like it's pretty straightforward. Oh, I bet you have Superland. It's relatively straightforward. I mean, it took me a while, obviously, because it's easy to get these details wrong. I think also the way I'm doing the clock stretching here thing might not be necessary. I'm just gonna make this, by the way, again, which should prove to me that it works. The fact that we get any video out of it at all, by the way, is enough to prove that this is correct. So, pretty happy with that. Also, I have a to-do here that says if the monitor is disconnected, how do we detect that? It turns out there is actually an interrupt line that comes from the transmitter. I haven't looked into how to use it, though, so I'm going to leave that to-do there. And then this enable video output data generation. I was thinking that I would have like an enable or disable for the display hardware, which is the part that takes the pixels out of memory and actually sends those to the transmitter, which is separate from this unit that drives the I2C part. But actually, I might just let that go all the time. So in this case, displaying it just does this stuff. I'll leave these as separate functions because this is kind of nice. So there's some cleanup there, which is nice. And then I'll just get rid of this too, because who cares? So that's mostly what I did for this stuff. Chief Sector says the Super NT doesn't even start without connected HDMI, which makes sense. Yeah, maybe they're doing something similar because we could, for example, I mean, we could start doing other stuff when this wasn't connected if we wanted to, but it's just easiest if we just do this. The other thing we have to do is we have to watch that interrupt line because there is also the case where what if I disconnect the HDMI? This has no way of knowing, and so if I disconnect it and then reconnect it, the transmitter will shut itself off. It's a power saving feature, and I think you can actually disable that too. But the only way to disable that, as far as I know, is to wait for this to go high, turn the chip on, and then disable it. So we still have to do this anyway. Now, again, in simulation, I didn't actually emulate any of this interaction, so the CPU just hangs there right now, and I want to come up with a solution to get around that. I'm actually thinking, because this is probably going to be pretty general, where we have a lot of this hardware setup that we have to do in the beginning when we turn the system on, and actually I don't want to have that in the simulator. I mean, it would be nice to be able to simulate all of this stuff too, at least optionally, but at the same time, this stuff is actually pretty easy to verify against the real hardware, so it's not really necessary for me to do that in the simulator, I think. The bigger problem is that whenever I run the simulator, I get a trace output, which is really valuable for debugging, and I would like to not have all of this stuff, which is going to be the same every time, represented in that trace. So I'm considering having some bit in a register somewhere where you can read it and it'll tell you if you're in the simulator or if you're on the hardware, and that way I can just have one ROM that'll just dynamically detect and then give me more or less useful data depending on which environment it's running in. We won't do that now, but that's just a thought that I had. So that's how it looks like to enable the display from the software side. Oh, that's awesome, G Super. I'm totally going to call it the matrix bit, which is not at all going to be ambiguous when we actually start having a GPU, which makes it even more fun. That's awesome. I'm so into that. Perfect. Okay. This is why you need to watch these streams, man. Okay, so that was that. What else? Yeah, the whole display stuff. So this, I'm actually extremely proud that I got this working. Like, I thought about it, I don't remember when, but at some point yesterday, it kind of clicked in my head. So I got to go back a little bit, because I was originally going to I was thinking 640 by 480, just because that seemed like a natural resolution. And it's also one that I've gotten this chip to display before. And one of the reasons why that's a good resolution is because a lot of monitors still support it, whereas if you go below that, they don't necessarily. In my limited experience, but experience enough. So I wanted to output 640 by 480. And so, of course, my original plan then was to to support that natively. So to have, again, a frame buffer like I have here mapped, but then pull 640 by 480 by 16 bits out every frame. But I actually did some math on this. Hey, Aaron the German. That's the docs, G Superland. That's what it is. But yeah, I did some math on that, and I won't repeat all the math because it's basically based around, like, I took some traces of the CPU reading memory, and to see how long that latency was. And typically when the CPU reads memory, it takes like 20 cycles for us to get the data back. So there's like a 20 cycle latency. Now, the memory controller actually gets way better latency if you do a bunch of reads in a burst. It gets better latency and throughput, so like that isn't actually necessarily an issue, but at least the patterns I was looking at was like worst case. So worst case, we'd get like 20 cycle latency or something. And I also wanted a little bit of slack in that just in case we couldn't start them right away or something. So what I was thinking is that the display hardware would kind of block out the bus so that the CPU couldn't access it for basically the entire period of a scan line. Because I could read 4 pixels at a time with my 64 bits wide data word. 16 pixels or 60 bits per pixel. And since I'm running at 150 megahertz and I'm doing 640 by 480, that's 6 cycles per dot. And then if I'm displaying 4 of those, that's 24 cycles, which is just above 20 cycles for the read latency. So if I started 4 pixels early, then I could essentially read all of the pixel data as we go along, and display it kind of on the fly. And that, I don't think that's a bad scheme. The problem is I did the math for how long the bus would be blocked every frame, and it actually turns out we'd be blocking the bus for about 75% of the frame, which means the CPU couldn't access it at all, which would be really, really shitty. So then what I started to think, well, what if we double buffered? So what if we had a line buffer in memory internally? And then what we could do is we could start a line early and just do a burst read into that as fast as we could. And then as we're displaying the next line, we'll have a second line buffer that then we can fill. So we kind of do these alternating line buffers where we're reading into one with these bursts that are definitely going to be faster. And then we're reading out of the other one at the same time. And this, when I did the math for that, I think I assumed that instead of getting 24 cycle latency, you'd get 20 cycle latency. And so with that, we still end up spending like 60% of the frame. Just assuming everything would work, I just kind of did the math for it. We'd spend about 60% of the frame reading data out for the video. So I thought that wouldn't work. And then I actually just Googled like typical PS1 game resolution, or like, I didn't find anything for that. So I think I Googled, what's the game with Snake in it? Why am I misremembering this? I feel so terrible now. How can I even be a 90s kid if I don't remember what game that was? Metal Gear. It's Metal Gear. Metal Gear Solid, exactly. Yeah, so you're absolutely right. So I Googled Metal Gear Solid resolution, and it actually runs 320 by 240 in 30 hertz. Now I still want to do 60 hertz, which is what I'm doing now. But so then I just did the math for that. If we still do that double buffering scheme and we do all the burst reads, and even if they're 20 cycles per read, yeah, I need to leave, don't I? Then we end up spending about 15% of the frame reading out data. And I thought, well, okay, at least that's acceptable, and it gets us to the right kind of resolution that we want for this system. So I was pretty happy with that. So that's actually what I implemented. And that's why it ended up being kind of complicated, was because I was really trying to reduce the amount of bandwidth we waste just pulling pixels out of the frame buffer. So with that in mind, it was kind of complicated how all this works. It's best if I draw it than if I show you the code, because there's a bit of stuff going on. I can show you some of the timing, because for me, it was difficult to implement this. It was a lot to keep in my head, but I loved it because I got in total flow last night and just did it, and that was my whole evening. But it works, so I'm really happy about it. And I made a lot of mistakes along the way, but that was just mostly dumb things. Oh yeah, good call. I just love that that's the actual system running this whole time. It also gives me more of an opportunity to watch it while it's being tested. So essentially what we have is we have 2 line buffers. And each one of these, so this is the other thing, as I'm still actually outputting 640 by 480. So in terms of the frame, we essentially need to output 240 lines, but we actually need to output 480. So what we do is we split each line up into 2 lines like this. This is a great diagram, you guys. Perfectly representative. And so what we do is we dispatch actually 2 lines early. We dispatch the initial reads. And then what we do is we say we read data into this buffer while we start displaying out of this one. But of course, initially it doesn't display out of anything. So then when we reach here, this buffer is filled with a bunch of pixel data. And so then we're going to display out of this buffer twice. We're going to do it once for this scan line, and then we're going to do it a second time for this scan line. And while that's happening, we're going to dispatch a bunch of reads that go into this buffer. Now those reads are, is the output at the back? That's the backer for the face cam. Yeah, I'm doing that. It's important. Put this here. What up? I am in the Matrix, you guys. It's got to be a line better than that. Really? There we go. Whoa, I'm in the xenowing. Oh, this is the best stream, you guys. But yeah, the caches also help with perf because, again, we do the burst reads. So these actually fill up quite fast. And we'll see that I think I can actually remove one of these buffers. I don't actually think we need to double buffer because it's so fast, but I want to check that out. Of course, I sound like a teenage... Man, I'm bad at talking today. Of course, I sound like a Teenage Mutant Ninja Turtle. What the hell do you think I grew up on? Anyway, so I think these fill up actually quite fast. And we have... This isn't actually a complete picture of the frame because there's blanking periods as well with this. So it's actually more like this. It's 800 by 525. I don't know why I wrote that vertically. So there's these blanking periods, and then also somewhere in here you have like the H syncs and then the V sync, something like that. I think that's a good way to draw that. Also, of course, I'm going to Tursock, by the way. It's my favorite party. It said so in the invite. So yeah, I think we'll need to double check the timing, but I think we can actually get away with removing this double buffer. But anyway, that's how it works, is that I have these 2 line buffers. And there's additional hardware units. So there's the display unit. Yeah, I look forward to seeing you guys there too. There's the display unit, which is doing all of this. It has these pixel counters. It has an X counter and a Y counter. And it has an internal counter also for where it reads out of these buffers. There's 80 words in here, so it counts up to 80. And then, of course, that happens twice. And then there's also a couple output signals for when it needs to start reading, and also which buffer it's selecting, which determines what the other hardware that's fetching and pulling into this is doing, or where it's writing to, and then it also determines where we're reading from when we actually get the display data. So that's kind of the gist of it. The other piece of hardware are the ones that are fetching data into this again. And I think I called those, what did I call them? We can just look at the code. It's mostly Python and then some Verilog to tie it all together. Yeah, it's the load issue and load return units. And I did it as 2 units because we don't actually know when the loads are coming back. And it's easier to have it as 2 units. So essentially what we do is we have a pulse, which happens around here. And it happens every 2 lines, which actually I think it happens here. Is when the pulses are done. And as soon as that pulse happens, we swap which buffer that we use. So the buffer select inverts. And then we also fire off a begin signal for the load issue and load return. Now load return, it just basically resets a pointer into this. And all it does is it watches the bus for data to come back from reads. It doesn't actually know that the reads, or it doesn't concern itself that the reads are happening. It just knows that data is going to come back. And every time it comes back, it does the write, and then it increments that pointer. That's all that does. So load return has a start command. If it does that, it resets the counter. When it gets the data, it puts us into here. And then it also just has some output signals, which we route into the write port of that buffer. That's it. And then the load issue is the one that's actually dispatching the reads that are going to come back. And so what happens with that one, it's a little bit more complicated because it has a frame buffer base. So when it gets this start signal, it resets this next word counter here. And let's see, what else does it do? Yeah, there's also another one that's just the bus readouter address, which I think the main video unit, I actually drew this wrong because I think I have the blanking period up here, sort of, so it's effectively before the data, not after, before the frame, not after. And I think I dispatched that on this line. I think I just hold it high the entire time that line is the current line, because that's good enough. And then that actually resets this bus read address. And so then whenever this is dispatched, whenever it gets a start, it has this next word counter, which is the right pointer into this buffer. And then it's going to count that up, or it's going to issue reads to the bus. And then as soon as for every successful issue, it will go ahead and increase the bus read address. So it'll read the next pixel next time, and it increases the word counter, which again is the buffer write address. And then once it gets this start again, which is going to do every 2 lines, then it only resets the write address into the internal buffer. This one will keep incrementing for every pixel. G-Superland says, does the before frame approach cause latency between game state what's actually displayed? No, because you're only going to check the input, for example, once per frame anyway. And so whether or not you check it here or here, like if you checked it here, then you'd get that before this is displayed. If you checked it here, you'd get it before the next one's displayed. So it's like it's the same latency either way. It's rather than thinking of it as like moving the frame, it's more like which phase are our counters in with regards to that same cyclical thing that's going to happen anyway, if that makes sense. Which is also why we can kind of choose, and the receiver is also fine with that. It looks like the same signal. And in fact, actually, I might, it is more convenient to have the X offset like this, because if we want to issue reads at the beginning of a scan line, it makes sense that we have all this extra time to play around in. But I wonder actually if this is a little bit simpler if we move the vertical part to the bottom again, because then we can always kind of dispatch everything at 0, 0, which might be nice. Yeah, they are going to have capital opinion on that. That's great. But yeah, the main reasons why we want to reduce bus bandwidth is it's a shared memory architecture. So this memory bus has to be multiplexed between shared between the CPU, the GPU, and the display unit. So the display unit's again just pulling pixels out of memory to give them to the screen, and that's very timing critical, so that one always has priority. Then the GPU needs to put data into this frame buffer, which is going to be a faster way to do that in the CPU. So I think I'm going to give that priority over the CPU as well, because the CPU is mainly going to be driving that. And then the CPU has the lowest priority. But it's essentially that kind of priority. That's all it really does. If there's any activity requests from the display or the GPU, then whatever units above that just gets blocked out. So it's just a couple muxes in terms of that priority encoding. So that was another thing that I had to do is made it so that the load, issue, and the return units could be hooked up to the same bus as the CPU and make that work, which is fairly basic actually, because you essentially have something like this, where you have the actual bus down here, and then you have like the CPU, for example. This weird looking upside down shorts, and the display. And there's a couple things missing from this display interface because it's only doing reads, whereas the CPU is also doing writes. But it doesn't really matter, because if we're doing a read or a write, if the CPU is trying to read or write, that will be blocked by the display. So essentially, both of these just interface directly to the bus as they think it is. But there's this ready line that actually the bus exposes, but then we can also exploit. So we can basically say if the display is trying to do anything, then we're just going to tell the CPU that the bus isn't ready, and then block all the CPU signals. So that way this bus gets interacted with the right way still, and then both of these just interact with respect to that busy signal that they have to worry about anyway, and we kind of get this arbitration for very little logic. The only thing is that when we issue a read, we put that into the underlying bus, and then when we get data back, we need to know where that read came from, so that we can issue that data back to the right bus master here. So what we do for that is we just have a little FIFO in here. So every time we get a read from either source, we're just going to put a 0 if it was the CPU and a 1 if it's the display, or maybe I did it the other way, I don't remember. And then as reads come back, we say, okay, we get a read back, then we pull this first one off the FIFO. That's a 0, so let's get that to the CPU. Another read comes back, we see that that's a 1, and we do it like that. So really, really basic. Definitely G Superland. And then on a thousand times on a whiteboard, I'll write that I did not actually do that, or that I will not do that. I'm so bad at this. Anyway, so that's mostly how this works. But here's what I'm thinking. Now that this is implemented, we can actually look at some traces that I got here. So if we go to record this again, and I'm going to open up the signal tap. This again is our baked in logic analyzer. So I tapped onto the bus here. We can see a bunch of different things because I was kind of debugging here. So here's our pixel clock outputting pixels. And it's going to be 4 pixels per word, per data word. And here we can see this is where the load actually gets kicked off here, kind of at the end of the pixel clock. The pixel clock is again, it's 3 low and then 3 high pulses per the actual system clock, which is correct. And I usually will end up sort of dispatching everything before this, so it's generally ready with this falling edge of the pixel clock, so that we have the maximum time, the receiver has the maximum time for the signals to settle on its end before we give it the rising edge. So I want to line everything to this falling edge as much as possible. And I think I might have a couple signals that are a little bit late, but we need to put them in the signal tap to actually verify that. And this, it looks like we only get 3 lines, but there's some important things here. Actually, this should be 6 lines. The important things here is that we can see this buffer select, and we can see that it inverts every 2 lines. We can see we issue a new load every 2 lines as well. So this logic appears to be working correctly. And really importantly here, critically, we can see this is what the loads actually look like. So they come back pretty fast. We issue, this is a read request, so it's requesting reads all the time. And it looks like it gets in 2 read requests here, and then we get the data back here, but we can issue more reads within that time. So here we can still see it's 1, 2, 3, or here, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21 cycles latency there. But you can see, because we're able to at least pipeline these issues, that the data comes back fairly regularly after that. So we're able to pipeline a lot of these. So this should be 80 of these, and something happens here. This is probably the bus. This is probably the memory controller doing a refresh or something. So we don't actually have access to the bus for that period, but that's fine. So you can see we're issuing for, what is this, like 700 cycles or so, and over 6. I mean, this is rough, but so we're doing issues for 700 cycles, and then divided by 6 per pixel. So for 116 pixels worth, we're doing the issues, and then we get them all back here, a little over 768. So even if we round that up to 900 to be like really conservative, let's say we read all of our pixels in 900 clocks times 6. That can't be right. No, it's divided by 6. 900 divided by 6. Then we've spent 150 pixels actually reading all the data. And if we look at the I don't think that's the front porch, but the blanking period before the display, that is exactly 160 pixels wide. So what's nice about this, and what I'm suspecting I think will actually work out here, that all of the reads actually come back in about 150 cycles. But that's all of the reads for the end of the line. We get the reads for the beginning of the line way before that. So we actually have quite a lot of slack here already for reading the entire line before we even have to display any of the data. So So I think this is during the blanking period, which is the front porch, the pulse, and the back porch. I think that's what that is. Maybe I'm mixing that up, but anyway, we actually have a lot of time. So I think what I want to do is I want to actually remove this double buffering, because it looks like we can just read into and display out of the same buffer every time. So we'll still issue the reads every 2 lines, but then we won't have this buffer select or the other buffer, and everything should just work. And in fact, I talk a lot about the C64 because I just love that machine, but the VIC-2 and the C64 is actually doing that as well. It has these character accesses. Okay, then yeah, it's the front porch is on the end of the line before H-sync, which in this case, because our H-sync is here, then this is our front porch, this is the H-sync, and then this is our back porch. So it's actually this entire period, which is, I think, the horizontal blanking period. It ends up reading all the data until about here. And again, we could read all the data until out here if we wanted to, as long as we have the final word, as long as we have all the words loaded before we actually start displaying them. So this should be just fine. But yeah, the VIC-2, it has an internal character buffer for the character data. So it loads all the graphics accesses. So like it does this character display. Let me actually pull some of this up. I like talking about this chip. So I actually want to find one that shows like a lot of the characters. This is a good one. Here we go. So this particular picture here, we can see that this is 320 by 200 is the active display area. Of course, there's more in the frame because we have these H blank and the V blank intervals as well. What's important here, though, is you have this character display, and this particular video chip, all it really does is it knows how to display a row of characters, and it just happens to do that a lot. Similarly to how my video chip really just knows how to generate some timing, but also just knows how to go and read one line of pixel data and then display that twice, right? There's like a unit that loads pixel data. There's a unit that displays pixel data. So the unit that displays pixel data just does the same thing the entire screen. The unit that loads is just dispatched every other line, but it just loads new data. So it's all these really, really simple units working together. And this is very similar. To display characters like this, you need the index of the characters, which we call the character data, and you need the pixel data of the characters for that given line, which we call graphics data. And the way that the bus on the C64 works is that on the rising edge, the CPU uses the bus, and on the falling edge, the VIC uses the bus. So it actually gets the pixel data for these given characters like a cycle or two before they're actually used. And you need to do it a couple cycles before to make the scrolling a little simpler, but essentially it's loading on the falling edges there. It loads all the G axis, as we call those, where it loads all that data. But then every 8 lines, we need to load new character data, and it could load that every line. In fact, some graphics modes will make the hardware do that and exploit that. But what that would mean is, because then suddenly the chip needs to use the rising edges as well, it blocks the CPU out, so we lose CPU time. And those are called bad lines when that happens. But what's really doing is it's also loading the character graphics in addition to loading the character data, in addition to loading the graphics data, which it would already do anyway. And again, that as well is just the same kind of idea where it loads the graphics data into an internal buffer, and it also displays out of that same buffer. As long as the loads happen before they're being displayed, that's fine. And the only reason it does that in an internal buffer in this case is so that it only has to do it once every 8 lines, so that it can free up the CPU to have access to the bus for the other 7 lines, which similarly to the reason why we're doing buffering, in fact, it's like exactly the same. It just allows the CPU to have more of that time. So we spend less time reading data, especially if that data is going to be used again, which it is going to be used again because the characters don't change, just the pixels relating to those characters do. Kind of a long-winded explanation, but there's a definite parallel there. So I think it's quite relevant. Now, I think if we were doing 640 by 480, maybe we wouldn't get away with this. I think we actually still would, though, because assuming that these would be doubled, then this would still be out to like here. So I think we'd still be okay. And that's again, now that I've built it, I can actually look at this and see that that's kind of obviously the case. But before I had built it, it wasn't as obvious. So glad I implemented it this way. But now we can simplify a bit, which this would just be less hardware then. Yeah, Daniel Collin mentions the DMA on the Amiga. Oh, I love this document, by the way. Oh yeah, this is how it's allocated per horizontal line. Yeah, there's more stuff doing DMA as well for the Amiga, I guess, like disk DMA, memory refresh. There's also a cycle. I think it's only one cycle that's dedicated to refresh on the VIC, or maybe that's even. I don't remember where that was actually. But there's also a section of the line that's for sprite DMA, and there's a section of the line that's for the C axes, and then the G axes are all on the falling edges. Pretty cool. Much more pretty than it looks extra pretty in comparison to my lovely diagrams here. Also, look at my great use of negative space. AKA, I just forgot to draw on that side of the screen. But yeah, my guess is that we're going to be totally fine with just a single buffer. And the way that I'm going to verify that is I'm going to go in here and just remove the second buffer. And let the compiler tell me what to do. So I'm still using my own Python language here, which I'm super happy with, by the way. It makes this a lot easier for me to reason about this stuff. But I still haven't implemented module instantiations in the language, so I end up creating all the module definitions in Python, but then I still tie them all together in Verilog. And that's fine. I don't really care. I'm the only one working on this, so it's not like it's a problem that it's half and half as long as I don't care. But of course it would be nice to have it all in Python, which I think would also save a lot of lines of code where I'm just like defining essentially wires that we that we fan out the connections to the unit out into, and then reference these later. So I think there's going to be a lot of some kind of cleanup that we can do. But anyway, I have these display buffers. Here's the buffer 0, buffer 1. Also, these are also implemented in Verilog because I also don't have ways of describing memory elements. Which in Verilog you have to write some events that are going to happen that sort of mimic the behavior of memory cells, and then it will infer that that's what you meant. But in my language, I want to have like explicit definitions for that. Which, by the way, I think I can actually make a simulator that's faster than Verilator with my own language. But that is a complete other thing that I would love to look into another time. But I'll probably look into it pretty soon anyway because I'm thinking about it. Obsession's really fun. Anyway, this display buffer, all it is it's just memory elements. And I don't actually know if I need to make this a power of 2. I assumed I did. I didn't even try to not. Maybe I'll do that later. Because I only need 80 words here, not 128. But we're gonna half the memory requirement for this anyway, just by removing that other buffer. So we'll just get rid of buffer 1 here. And I think I did display buffer 0 here for all this stuff, which we're just going to call display buffer now. And we're going to remove this. This display buffer select signal also goes away, so I'm going to go back and forth here between this and the display hardware, which is just in this one Python file here. So here we have this buffer select, which we're just going to get rid of because we don't need to do that anymore. Easy. Yep, and then we don't need the buffer select stuff here. So in this case, we will always read out of this buffer. And also that's kind of nice because then we can just kind of inline some of this stuff, not fan as much of the stuff out either. And the data as well, I think, gets assigned to, that's write enable for this buffer, which is always just if the data is valid. Yeah. That might be it, actually, for that part of it. In fact, that might be the whole thing, which is pretty cool. Let's see if I'm right. We're going to make... The other thing about my Python language is that it will output a bunch of not used warnings, which I've decided I'm just going to have very later ignore. This says, what are we missing? Signal definition not found. Display buffer adder. That was this, which should have come from here. Oh yeah, display buffer read adder is what we want to do. Because this has display buffer adder, because in the display it only cares about reading, so I don't call that a read address, it's just an address. Right, because it's fanning out like that. If we do this, then that should just work. And then here's all those warnings. And I also want to read this because this should, if we look for any in the xenowing, so here it says signal not driven display buffer data, so we need to actually be cognizant of that. This was 161. That's this one. No, display buffer data here. Which I think since we already hooked this up with display buffer read data, we're fine. So I think that's just it. And I don't think it tells us anything else. But yeah, all this stuff here where it's like this clock reset we don't need there, but I should have actually written those. That'll go away when I move that into Python, and then all these warnings in the generated code I know are actually correct. So that's fine. So this seems to have like built. I'm going to do a make test, which takes a while right now. It actually opens up a mini FB window, which is off the screen right now, and I can't drag it because it doesn't update the window until it actually gets any data, until it gets a vsync pulse. So I'll have to wait. And it takes a while to... Whoop! I think my video just went a little shoddy, by the way. Ugh. Oh no. I'm gonna wait for a second while the stream comes back. Yeah, the Verilog sim just kills my CPU. So let me know if it's good, guys, if we're back. I don't know if I can set the affinity for the simulation. I probably can. That's what it is. It's the simulation that's the issue here. Hopefully it doesn't happen now when I refresh this. I'm just going to zoom in because essentially most things should look the same except this buffer select goes away. So now we're going to load. We essentially just generated 2 gigs worth of signal data. Just CC? I don't know that. What is that? But yeah, we just generated 2 gigs of trace data, and now we're loading it into this waveform viewer. It should all look the same. Except again, this buffer select will go away. And it does. Everything else is identical in this case, which is what we expect. And now what I want to do... Well, again, it's not compiling that killed the CPU. It's simulating that killed the CPU. So I don't know if Verilog will... Or if Verilator has an option to max out the number of cores. I honestly don't know. But that's what we would want to do there. Anyway, before I recompile this on the hardware, I'm going to open up SingleTap again because I think I had this buffer select again, which we're just going to delete because that's no longer relevant. And I actually want to add a couple other signals here before I start. And hopefully this compile won't also eat up the CPU, but I guess we'll see. So I'm just gonna, by the way, I still love that the xenowing's running in the background of me. You can see how good my green screen action is. All right, so in here, the xenowing, we have the display. And I wanted to, actually I want to look at the display buffer, which we might actually have to do analysis first for this. Actually, I don't think we have to, because I just want to look at the display, and we can do the, I want the buffer address here, which gives me the address that we're reading from. And then there's this display load return, which has the load address here, which is where it's going to write that data into. Yeah, that's correct. Those are the signals I also want to have in here. We don't want to trigger on those. I'm using too much memory. This should be fine. Good. So then I'll recompile, and this will take a while. But then at least we'll be able to actually double check that this works as expected. Oh, I'm disappearing into the matrix. Get up, Trinity. Get up. I need to see that movie again. But yeah, I was really happy and proud that I was able to get that double buffering to work and everything. Of course I see myself as Trinity. I can identify a female not leads. You picturing that is your problem and your fault, I'd like to point out. I take no responsibility for that. Yeah, I was proud that I was able to get that to work. But I'm happier if we don't need the double buffering thing, because, again, it's less stuff. And I always like less stuff. Simpler designs are better designs. And then the other thing that I still want to do is I want to just make sure that all the issues that we're doing and everything, like all the load issues and everything, are timed as well as we expect. That's actually another thing. This wasn't all I wanted to remove. Now that I thought of that, we also are still starting to issue 2 lines early. See, dispatch new pixel loads at the beginning of all scan lines. 2 scan lines early. We don't need to do that early anymore. We do want to skip the last 2 lines though, or actually want to skip the last line is what we need to do. So yeah, so this should actually be 45. And as long as this is less than 5, it goes up to 525. Yeah, actually it's just this, because we get every other line anyway, and we don't skip anything because we're not preloading. So so 23 and 24 it will display. So I think it's just this actually, which is even better. Well, I'll run this first, and then I'll make that change and double check. But yeah. What am I thinking in terms of CPU and caches and stuff? I'm considering adding a CPU instruction cache at least. Maybe a data cache. What I'm thinking right now is to put that off and not do anything about it for a while. And then I think that will be a nice speed optimization later. So far it hasn't been something I've decided to do yet. Just because, again, I don't it's going to be another source of complication. And I'm much more interested in working on the GPU first. So eventually I would like to do CPU caches. I'll probably implement caches before I implement pipelining for the CPU. The GPU, I think, will be, with what I have in mind, it'll be designed, pipelined up front. So depending on how simple I make that, that won't be difficult at all. And that'll just be the natural way to do it, I think. So, but definitely because of this memory latency that we saw earlier, caches would really help. Essentially every time we hit memory for reads, because we don't have to wait for stores to come back. So whenever we do reads, that's a 20 cycle latency at least. So the GPU, I want it to be a basic rasterizer. The first thing I actually want to do with it is clear the screen. I don't think I'll expand on any like blitter-like functionality beyond that. So clear the screen is probably the first thing I'll make it do. And I wanted to do a triangle rasterizer. And first I'm just going to do flat shading and no texturing. So it'll just plot whole colors. Once that works, I'm considering also doing some basic texturing where I have a texture cache. So I'm thinking that the texture cache will be in the GPU, inaccessible to the CPU. And I'll probably have a GPU command that says DMA into the texture cache from this range. And that's how you would actually get it to load that. Because that would be way faster anyway. And then another GPU command would be render and some internal state to the GPU, which you probably also have to put in the command list to change that state. Would be to actually do texture mapping from that cache. If that cache is relatively small, then we can just do one cycle access on that and no filtering. I also want to do everything with integers. I'm thinking 16 by 16 fixed point. And yeah, that's kind of what I'm thinking so far. After that, I do want to have some kind of shader support, which I'll probably initially implement kind of register combiner style, and then just sort of expand on that. Maybe I don't really know yet, but the way I'm thinking at least is how the pipe will work, and that getting clear through that pipe is kind of the first vertical. Please at least do subpixel. I will not at first. Only because I like that really chunky look. It makes it extra authentic for this kind of console. But eventually I probably will want to do it because it does look like ass if you don't do it. All right, we're going to go way in the matrix here as we put this on the device. I'm guessing this just works, to be honest. Oh, whoops. I started loading the... Can I stop this? No, I can't. It's too late. I started loading the... Can you guys even see the programmer? That's back here. I started loading the wrong image. I started loading the persistent configuration file where I really just need this quick one. Okay, so this works. As far as I'm concerned. It looks like it works. I'm guessing this is exactly what we wanted. Yeah, everything gets really shaky without it. And honestly, I want that for the first iteration. I think that'll be fun. Of course, we're not running with signal tap, which we want to do. And this is really cool because now we have this logic analyzer built in. So when I do this, then it already got a capture because the condition... Oops, I just realized you guys didn't see that, so let's do it again. We click this, and it gets a capture right away. And the reason it gets it right away is because this hardware is running all the time. So in particular, what I wanted to look at is this. We can see here, this is the buffer address, which is where it's reading from to pull out pixel data. And notice that if we zoom in here, there should be 4, 1, 2, 3, 4, actually 8, yeah, 5, 6, 7, 8, because it's 320. So if we have 4 pixels and we double those 4 pixels as well for our 640 by 480 display, but we're only displaying 320 pixels. So we're reading 64-bit words from that buffer. So we display the first 4 16-bit values on every second pixel clock, and then we increase it. So we're actually starting to display around here. is when we actually read the data. And you can see that all of the reads have filled up the buffer well before we even get there. And again, we basically have until here or so to actually fill everything, as long as we're filling this buffer ahead of when we're reading it. So that's why I wanted to add these addresses. You can see these are the load addresses where it's loading into there, and we get this load 4F, which is the last one here. It's going to load into there, and then this is the pulse for when the data is ready, and then it's done. And you can see then we get this address here, but then we don't do any additional reads. So that's all done. And then again, we're reading from these addresses here. So pretty cool. This totally works. And again, we have a lot of headroom here, so I'm quite happy with that. But I do want to test this one more time because we did make that additional change. I'm not going to run this in the simulator again because that takes a while. I'm just going to do make on here, which will regenerate the Verilog files. It also built the simulator, but we're not going to run it. And again, this just keeps us from doing that like preloading approach and simplifies some of the scheduling. So if we have to recompile this again, which takes a while, but fine. Yeah, then with the GPU too, there's a whole matter of texture filtering, which I'm gonna not do it first, but eventually I might want to do it. The thing is, most of those features, in terms of the GPU implementation, shouldn't be terribly difficult. But it probably means that the GPU pipeline as the pixels go through it gets longer. The throughput should still be the same because that's going to be bound by our bandwidth into memory. But then the latency is higher. So really it should just be, if we have full utilization, then we're just adding like a few clocks of overhead. A few cycles of overhead, which shouldn't really matter, but practically speaking, it might. So a few cycles of additional latency shouldn't be bad. Per primitive, I think is how often we'd pay that. And again, how often we pay that depends on the rest of the pipeline implementation, how efficient that is. So a lot of factors here. But the way I would do it is, in this case, we'd have, like, I already know how I'd do it, because if we had the texture cache, we could put multiple read ports on there. I don't know how many we can have. I could try 4 and see if we get away with it, but even if we have 2, we can essentially read 2 texels at once. And if we could also decide to pack the buffer in such a way, no, I actually don't think we can. Well, yeah, we could, because we could do reads on separate lines. So we do one read which reads these 2 texels, another which reads these 2 texels. As long as we can read enough bits per read port, then that would work out. So we could actually read all 4 texels in one cycle. And then after that, so that's going to be one cycle of latency just to read that. And then because these memories aren't very fast. And then we'd have probably an additional cycle, maybe more, where we'd be able to do the blending. And the way I do that is you take the UV and the upper bits determine where the texels are read from. So some of those bits become your like row address and some become the column address. And then the lower bits determine your sort of filtering factor. And I'm going to do everything in fixed point, but that's fine if we have enough bits. And from there, it's the same as you would do it in software. It's these 4 multiplies, which you can do in parallel. But the multiplies have, again, long latency, so we might have to split that between multiple cycles on this particular FPGA. But that's fine. So then a couple cycles later, we have all the multiplies done, and then we do a final gather for the add, and then we're done. So it actually shouldn't be terribly complicated, and having a texture cache is going to really help. So that should be it. Of course, the details of that are going to be somewhat complicated, but I don't think they're going to be that bad. And that's kind of one of the reasons I'm excited to get to the GPU. I think we can get a lot done fairly quickly. And the coolest part about this approach too, one of the nice things about this shared memory architecture is that I can prototype all of that in software and then start kind of seeing, okay, what does my rasterizer actually look like? What does our setup need to look like? I've also been thinking about the way we want to do vertex transformations. And again, I'm thinking to do this 16 by 16 bit fixed point kind of everywhere. Because that 16 by 16 fits in a register. And it might be that we end up doing SIMD as well, where we can do we can specify groups or registers to be a vector. And again, I think I can have, we might be limited on that in terms of bandwidth through the actual register file itself, but maybe we can have additional register files for vectors. I don't really know how it's going to look yet, but thinking about some kind of integer SIMD for the CPU is basically my point. That will help feed that pipe. So it'll all fit together kind of nicely. And again, we can get something working without all of that and just do everything on the CPU and just start moving bits into hardware and see it kind of get better and progress. I think that's going to be really fun. Lighting I hadn't planned on doing, but it really depends on what we can get away with. I don't know how much stuff I want to support interpolating across the triangle. Maybe it ends up being flat shading, or maybe some kind of ground shading. I haven't decided yet. That's kind of the fun of it too. Because in that case, the way you do it is you could have like a shading parameter that you're also interpolating across the triangle, just like you would with the UVs. And that if you've done a rasterizer, which I'm guessing a lot of you guys have, it's basically the same that you do for the x coordinates anyway. And then we just need to apply that lighting to the texel that I described from the filtering. Ruh-roh. That didn't work. Why didn't that work? Oh no. Oh, that's good to know. I didn't actually know what the extent of that hardware was. Because there's other things like fog that's really common in these fixed function pipelines. I don't know how much of that stuff I want to support. It's up to me, so that's the fun part. And then there's the whole thing about what do I do with this? I don't know. Okay, something's wrong here. I don't know if it's not detecting the hardware. In fact, I have no idea what's going wrong here. Okay, so we're running this, and so the display hardware is still reading stuff out of memory here. So we're still getting traces, so that's still working. But we're not getting any video signal. And I wonder, honestly, if it's just the connection with the HDMI connector. Doesn't seem to be. The other thing that happens with this a lot is we actually have timing violations in the report here. And it really annoys me because it's always with these parts. It says CPU here, but this is the CPU inside the memory sequencer, which is really annoying to me that I have this generated memory IP that doesn't meet timing on this device. It really bugs the crap out of me. But usually these slack numbers are not that bad, and these are worst case timing analyses anyway, so like this typically works. But yeah. Exactly, G Superlin. I mean, that's the other thing too, is that obviously very quickly with a lot of these kind of systems, you very quickly realize like how much you're limited by lack of content. So like I only have 64K of ROM and I have no plans for any kind of storage solution. So I'm going to have to fit it into that, but I can still do some basic geometry, some really demo-ish stuff. So if you guys have seen, as a rough idea, if you guys have seen some of the virtual self like lyric videos that he puts out, I would love to do something like that. But then there's also like, what does the audio hardware look like and how would we pull something like that off without samples? I don't know. We'll probably end up with something shit, but it'll be fun. But why doesn't this work? That is the question of the day. So one of the things that you guys can't really see, but on the system itself, is I have an LED that I typically sort of pulsate as everything is running. And what's interesting here is that that LED is not pulsating. And typically that means we didn't get to the main loop. So actually if we go here, this is again the xenowing itself. And as I'm resetting this, it does tell me it's online. And I think if I go into main, that's the first thing it does, and then does display in it. Now it says time to try a random frame buffer adder. So I'm suspecting a power cycle might fix this. So I don't think it's talking to the, I think it's failing to detect the monitor, actually. Which is really kind of shit. Let me hook this up to another monitor and see if that helps. Actually, another thing I can do is I can disable and re-enable this capture card maybe. Which might help. It doesn't, but the xenowing is still responsive. So I've got a monitor over here that I'll just try. Don't get into hardware, guys. It's a pain in the ass. No, I'm actually loving this project. It's not necessarily how a game console would be built, but in today's modern world, it's how one could be built. Okay. That's turned on. Nothing. I really don't know what the issue is here. Because the weird thing is, I did a hard reset, but that probably doesn't load any valid code now because I like half loaded that other file. I'm gonna try that actually. Reflash that, which is fine, but I wanted to change this output file to be this one. And it's take longer to load, but at least then we'll have an image in there if I do like a hard reset. Power cycle. I don't know what the issue is here. We'll poke at things, see if we make any progress. In any case, I'm still happy that we simplified this hardware, but I might have to roll back that other change. I don't think so, though, because it looked like the relevant parts were the same. Looked like those were still working. So, because we saw that in the signals app that didn't change. So that should be fine. Again, XW Online. It's not showing me anything, though. Because again, XW Online is not the issue here. So this is with no monitor connected. Oh yeah, I killed my connection there, didn't I? That's the problem with power cycling, is that this doesn't reconnect. I might actually implement that where I can, if I detect that it's been disconnected, it'll just try and reconnect a bunch. That's probably useful for this tool. Yeah, we're not seeing anything, which is really annoying because I didn't change anything. This should be the same. Did I change the code? Don't remember changing the code, but whatever. No, code should be fine. I just remade the sim. It didn't really do anything. I should have committed before I undid this very last change, which was that, by the way. That was it. So let me just do a recompile with this again, because that's what we had. And if I can verify that that works again, then we can commit and then try to simplify that in a separate thing, which is probably a good idea. I can just amend the commit when we get it working. So the really annoying thing about when this kind of thing fails, it's really hard to know what to do. In this case, I would probably try and maybe snoop the I2C bus in the signal tap analyzer. And then we have slow iteration times, but at least we can see what's happening. That's kind of the worst part about FPGA development in general. Like, I honestly really enjoy the logic part of it. Nice cheap detector. That's how I feel right now, to be fair. Oh, whoops. Don't worry, I won't read it out loud. Or maybe I will. D-A-D. Dad. Jiffavanen kanen bfkkt vgdiga jiltfdiga bkth ogre. I dare you to do better. Monitor got impatient and turned off, by the way. Clipping this without context should be the title of my streams. Thanks, Bite for C. I have officially applied for permanent residence, by the way, which I'm excited about. Oh, wow, Grashev. Cool. Congrats. CPU or GPU? Well, I guess for GPU, it'd be in Trondheim. By the way, Dark Second, I just realized that the DE10 Nano has the same HDMI transmitter on it. I didn't even realize. Ah, cool, Grachev. That's awesome. That sounds really cool. Ferris having a normal one. Yep. Man, you clipped that precisely. Are you moving from Trondheim? That's great. Yeah, congrats. The most quality content. This is what you get. This is what you guys sub to. Palm to Pimp, what's going on? But yeah, if you ever try to port the xenowing over there, that should make it easier. But I don't know if the D10 Nano gives you direct access to the DRAM. Yeah, Ferris reads Chief Detective's random tokens. That's the stream. But I guess you don't need direct access to the DRAM. What you need is access to, in this case, an Avalon bus. Which is what I'm assuming. Oh, I did the long one again, didn't I? Whoops. That's okay. Also what she said. Lord Capo, how's it going? You were the person who's new last week that subbed, right? I couldn't remember your name. But thank you so much. I appreciate that. Yeah, if it gives you an Avalon port, then you're fine. That's essentially what I'm assuming. But I'm also assuming that it's 64 bits wide. That has propagated throughout the design. So you might have to do some magic to get around that if it's not the same width. Okay, so this is potentially bad. I've configured what I'm pretty sure is the same image. And it's not working. I mean, the same image we had before. Uh-oh. This seems bad. Tells me to check the cable. I mean, what would have changed? I really hope something did not die. It's possible that I killed the video chip or something. It's not even warm, though. But here we are with the software side of this saying things are okay. Oh, shut up, Siri. That's not what I said. Siri being helpful as always. Yeah, this seems bad. I don't know what's happening here, you guys. But if I killed my FPGA, I'm going to be really pissed. Now I'm not totally dead in the water here. Like I said, there's things I can look at in terms of debugging this. This is concerning. Because again, this works fine. We have this here. So what we can do is definitely debug this from serial. You're absolutely right. In fact, we can bring back some of this debugging stuff that we removed before. In fact, I'll just grab that from Git. Why not? So let's see. If I go ahead and ROM XW source, no, XW. I actually need to move some of that stuff. Oh, that is in the correct place. Okay, so in display I have this. Where did I put that code? Oh yeah, it's in history. This one. ROM XW source display. And down in here I should have these debug reads, which I can put back in here. And we can print some of these. So I think I just had like these fixed registers, for example. And we can remove this. Well, we'll still have the sleep. That's a good idea. And we'll just try and do some of these debug reads. Is a good idea. And we're not getting anything, which is bad. Oh, you guys still see the overlay. Whoops. Let me fix that. That's probably like right in the way. And very useful because there's no signal. Put that behind me. Try to hide it. With my head. Okay. Why does this not work? So this is still trying to read this monitor sense thing. I actually don't know, or we put these reads before that, so these should have been printed before that. So reads are not getting through somehow. And the only way that they're not going to get through is with this clock stretching stuff. So if I remove this, it's still possible that it's actually doing clock stretching, but then at least it'll go through the motions. And we should ideally see something. Or not? That seems strange. What? I did change that delay, or at least I removed some code around it. Here it looks like 9800, so it looks like we got one of these, but why didn't we get multiple of these? Get and then get digit, which is just doing some really basic stuff. So again, get does all this stuff, write byte and read byte, which ultimately go down to these read bit and write bit things here. Read bit and write bit have nothing but delays, which they were all single ticks, which is why I got rid of that extra code. And this seems to work. But why didn't we get any other of these registers output? That's very strange. Also, it's different whether or not we actually get values back, which is odd. This might just be timing issues, you guys, which is what this has looked like before. But it's weird that it didn't happen before I made these changes. I don't like that at all. And again, if we look at signal tap, this still looks good. Clearly these reads are happening. Yeah, I might try to revert that code. It's probably a good idea. I think what I can do is I can do a git stash. That should do the ROM. And then I think we can do stash, which does still make some of these changes by like removing that other buffer and everything, but the software should still be compatible with this because that hasn't changed. So if we do a git stash, then we can do a git log, and then we can look at this, and we can check out this previous revision like that. And now if we go make, this is at least the previous software running on the same hardware. And again, nothing, which is obviously concerning. Nothing obvious here. Did I run this again when I recompiled? I'm not sure I did, actually. Just to be sure, I'm going to recompile now. I don't like this one bit. Cross my fingers, knock on some wood. Hold my tongue at the right angle. I'll try it all. I'm not pleased. And if this doesn't work, we can do a stash and rebuild all of that, which I would hope would help. That's at least what we were running with a little bit earlier. I also hate this because there isn't much to do other than sit here. If I rebuild this too, I'm going to add taps for the I2C bus, just to be sure. It could be single tap screwing with timings. That is possible. I've seen it before. I've had a lot more timing issues with this project than I thought I would, which is annoying. Typically, it's been stuff that I can fix, but when it's stuff within the memory controller, I can't change that. That's the annoying part. Though I've considered doing my own, which is not a great idea, but might be a fun one. Problem with that is that I would just need so much testing. So I would need to come up with a good way to do that. And ideally a good way to automate a lot of that as well. So, yeah, exactly, Lord of Capo. Well, I'm learning that now the hard way. The hardware way. Hard way. Like, the part I'm interested in is the digital logic part, and I'm having great fun with that. Having so much fun with that. This kind of stuff I'm not having so much fun with. Yeah, that's exactly it, Dinner Colin. Because that's the thing. If you don't get that right, then that's exactly what you have. I forgot to ask what you're working on, by the way. But yeah, we really don't want random memory errors. Now, the thing is, I wouldn't be driving the SDRAM directly. There is a PHY layer underneath, which actually will issue the commands and figure out all of the timing. So then I would be issuing lower level commands to the memory, but it's still opening up a world of hurt in terms of potential errors, because I'd have to, for example, ensure that that we're always doing refreshes. It's probably the biggest one, and then also need to figure out what the sequences of like states are that we need to have for proper operation of DDR3, which is just something I've never looked into. So I'm kind of interested in doing it from that perspective. Like, I kind of have this practical problem, which is that I often don't meet timing, and I know that the only timing errors that I even see are in that memory controller. So it seems like not the worst idea to try and go and fix that, but I'm also kind of interested to see what those commands look like. And then the other kind of thing that I'm a little bit interested in with that is the fact that if I did that, then I would have 0 generated IP in this project, which could be kind of cool. But none of that is critical to the project, so I'm not going to look into that for a while. Okay, so now I'm seeing my LEDs working. That's fading like it should be. And captures of this still look fine. Although here we can see the buffer address only starts changing here. And that might be because I think we got the 0th line, which would do that, because this still has the preload code. So I think that actually makes sense there. There is a global enable, but I actually have that latched. Or at least there's like a soft disable. Maybe that's not what you mean, but I do have that tied. I think it's a soft reset N, but I've tied that high. Not 100% sure that's what you meant, but at least I did catch that. Okay, so this is interesting because, again, the LED looks fine. And here we got past the init. Yet now I'm not seeing any signal in the capture card. Which is kind of interesting. Because according to this, the software has correctly talked with the transmitter, at least it looks like it did. And here we are getting no signal. So I'm going to try something else. Let's go back here. I'll just do an undo. Which should bring this stuff back, or redo perhaps. Yeah, undo. This will give us a bunch of these extra reads. So now if I make this, we get a bunch of debug reads. And you'll notice the timing's off again, which to me also again points to timing errors. because this has never happened. Like, this transmitter was rock solid before we started having stuff messing with timing. The values that are in these registers, by the way, look mostly good. In fact, they look great. I believe these are the values we should be seeing. But the fact that we see timing errors here and the fact that we're not getting a proper signal, that's indicative of timing elsewhere. Again, like, Quartus does tell me that I have these timing issues, but it's in that generated memory IP. And I tried to regenerate that too, and I got a bunch of errors that it didn't work. And maybe I just need to sit down and work through those. So we'll see that. But it also, in this case, disabling signal tap might help. It's annoying though, because I'm changing unrelated things. And this is what I get. This is what I get, you guys. Oh yeah, that's what you mean by those timing errors. Yeah, I do have the soft reset being driven, but I'm assuming that would be okay. And it's not. I think that's an output that's registered from somewhere else. Maybe not though. Yeah, it is really weird that there's so many of those errors. And I also had another project where I I basically set up the DDR and tested it in isolation. I have all the same errors with just that project. That's really frustrating. But maybe I just need to sit down and just try to work through that, because it's more annoying, or it's really annoying to have all these timing issues every so often. And the only way I know how to deal with that is to try again, I guess. But like I went through the wizard. I put in all the values from, like, it is a Quartus. It's an IP from Intel. And I went through the wizard from the example going through the example project that's provided by their site for this board. So maybe something is jank on here. I don't know. Very frustrating. But it might be, because I think I saw another example design. Maybe I'll just download that and try to put it on there. And then if I don't have those errors when I build it, then maybe I'll just copy that. Oh, I've seen the Twitter. White Quark seems to have a lot of fun with that. Yeah. And that's, again, like, a reason why doing my own controller might be kind of fun. But I actually don't think it would be fun at all. When I think about the actual job and the kind of state transitions. I have thought about, though, how I could test it, because, again, using this kind of UART or whatever, I could sort of pass, like, individual test programs that I could write in some kind of like really simplified CPU that all it would be doing was sort of feeding the memory commands, or rather, like, some microcode that I could put in my memory controller that would kind of do everything, and then just have some like high level control try to run against that. So I think there could be ways to set up like nice tests for that, but again, I would need to be really rigorous with that and like really be really thorough about what I'm testing, and or get really bad performance. Because like I could do a refresh, like every other command I just put out a refresh. But I guess you also have to do like wait states, which again I would probably bake into microcode in that case. So it's like if you get this stuff wrong, you're violating timings in the DRAM, and I don't think that you could damage it in the case of these chips. There's probably not issues with that, but the issues is that you'd get random bits being wrong or whatever if you didn't refresh, or bad state transitions. I don't know what would happen. So it's one of those things where I feel like I could do it, but I feel like for a free time project, it's a bad use of my time, because I would have to be so thorough. Yeah, exactly. You never know. I don't remember which version of Quartus this was. I should update that, though. That's another thing. 17.1.0, built 2017, so it's actually a couple years old. Updating that probably wouldn't hurt. Oh man, this is so frustrating. In here, it looks like this stuff is clean now. Yet I'm still getting no picture. Which is so frustrating because this worked when I started the stream. Ugh. This stuff is the worst, you guys. Oh, so I'm even a couple versions behind. Yeah, I should probably update. Hopefully that doesn't make it worse. Okay, so just as a small litmus test, I unplugged the HDMI cable and then I reset it. And because we always try to wait until we can sense a monitor, at least now, it never senses the monitor, so it never enables the transmitter. And when I plugged it in, it just turned on immediately, so it tried the frame buffer adder, did some fade babe. This should almost work, except again, we're not getting any signal here. No signal, it says. Now, another thing I actually didn't try is I could try changing the resolution here in case I mess something up. Don't think I did, though. But I still would have expected to see something in here. Which we're not. So that's annoying. Yeah, I also hope I didn't fry something. That would be really annoying. But I'd be surprised if I did, so... Yeah, that's what I'm thinking, is that maybe I messed with the timing a little bit at the same time. I don't think so. So again, I could test that. Stash everything. So this should be what we started with today, with those initial changes that we made to the ROM code that just removed a bunch of stuff. We'll try that, and if that doesn't work, we can reload the ROM from what we had before. Again, it's interesting because now that I rolled that back, we're at least seeing, or the CPU at least sees the monitor, and again, we're able to read correct data over that I2C bus. Yeah, I don't think that was a G-Superlin because I did build this today. It could be. I'm not ruling that out entirely, but I think it's unlikely. Though I've definitely made that mistake before. That's very frustrating when I'm just trying to simplify this stuff. But I should definitely go through that where I update Quartus, update the IP. See if I can kind of recreate that initial DDR3 test on its own that I had before, but with a newer version of that controller, and again with the same timings for my board, and see if I still get errors there. If I don't, then migrate all those changes into this project. Even if I have to rebuild all the top level stuff, I don't really care. Most of it's just pin assignments anyway, to be honest. And that's all textual in the Quartus file, so I could kind of plow my way through that. I'd be really surprised if I fried something on the inputs of the HDMI transmitter, because first of all, I'd expect that there'd be a decent amount of protection on this board, and second of all, I'm actually running it so this transmitter can accept signals from 1.8 up to 3.3 volts, and I think I run all the signals on 2.5. And I guess it's possible that it changes I/O standard when I was programming it or something, but like, that seems strange to me. And I do have two monitors in the sense that I'm testing both with my capture card and this monitor on the side. And with both, it didn't work now. So I think that isolates something wrong with my code or the board at this point. I've also never had any issues with that until right now, which, I mean, that could be how this goes. But from a problem-solving standpoint, I should at least consider that less likely. But honestly, even if it works now, I think I'm going to, after this build, I'm probably going to turn off the stream and do a little bit of debugging after that. But if we see it working, then I'll just kind of redo these changes. Yeah, it is a bummer to mess up midstream. Because I feel like we were doing good work. But at least at least I shared the stuff I wanted to share. Still happy about that. So for the most part, this is still a success. It's just this part got really annoying. So again, so if I reset really fast, we only get this message because there's that delay. So that's just like resetting it within that period. So that's like normal. I can also change the file again to do this one. The reason I'm loading this persistent memory is that then I can actually power cycle the board, which seems like a nice thing to do right now. And I want to make sure it loads up with the same image when I do that. Seems like a good idea. Should probably have enabled verify, but I don't think that's the issue. Okay, so I just now power cycled the board with this image, and it works now. Deep breath. Deep breath, guys. Okay, at least we're no worse off than we were at the beginning of the stream today. Stupid. And I can reset a bunch, and this should still work. Yeah, I would love to have a fix all problems checkbox. That would be great. That would be great. And actually, we're a little bit better off than just the beginning of the stream today, because we did commit this, clean up this display init code a bit, which is right there. So we do have that commit under our belts. If I do a git stash pop, oh yeah, this CSV or whatever, you know what I can do is I can do git checkout. I can just check out these timing things because that's all it really is. It's just outputs from this. In fact, some of this stuff I should actually get rid of in the repo, but I don't know. It is actually useful to have the results of the last build. I guess I don't need that in the tree though. That could just be local in my file system. But at least when I made this initially, I had no idea what was what. So I just threw it all in there, and then removing it's fine. I don't care about having like a super clean history. This is, again, a personal project where I'm learning a lot of this stuff. So who cares? But yeah, nothing physical is broken, it seems. So if I git stash pop, that's what it's going to do. Then we actually want to look at the diff. Now I'm going to do one thing though, and I'm going to check out Cordis, xenowing, the signal tap file, because the signal tap file is textual and it'll produce a really long diff if I include that. So here, just look at our changes. In this case, you can see I add this debug printing because that's what I was playing with. That's fine. I'll leave that in there for the next little build. In fact, I just won't rebuild the ROM and then we're fine. And then here is just these small changes. So again, I removed the buffer select because I removed this other buffer, which should be fine. I think that's actually all that's captured here. It's just removing that buffer. So the only thing that really should have changed in that case is timing. So what I'm going to do is I'm going to do make again, which will again compile the Verilog from the Python stuff. I just realized again you guys can't see this, it's behind the xenowing, but it doesn't really matter. So that's that, and then I'm going to open signal tap because again I checked that out, so now I want to open it so I can disable it. It's not enabled actually, which is good. I'm just going to build it again. Yeah, I'm happy to see it working again too, to be honest. But in that case, it's probably timing issues, and then again, more motivation to actually look into that. I think I complained about that last week on stream as well, that I was having those timing issues. In fact, I didn't even know to check the timing analysis until really weird stuff happening because I was violating it a lot when I rebuilt the CPU. I had a really long path from the input to the register file all the way down to memory issues because I had some things messed up there. And then a colleague of mine, because we have an FPGA team at work, suggested I check the timings, and he was right. But again, the annoying thing is that this IP always generates warnings, which sucks. But at least if we flash this again, if we build this again and flash it on there, I could do the slow path again and then reset it. And then if that works, I'm going to commit it. And then I'll try again to simplify that load timing. So I think we probably won't see it here, but I actually think, well, I guess it doesn't matter that we issue the reads early, as long as they get to where they need to get by the time we need them, which should be the case. This capture card's great, by the way. Deep in the matrix down here. But yeah, after this build, I'm going to go. Because this is a long stream. I also might stream for a little bit tomorrow night, just for a couple hours, but I don't think I will. I kind of want to, but I've been working really hard on this project in my free time lately, and I'm really happy with the progress. That's kind of why I've been working so hard at it. But be nice to rest, play a video game or something. Not on stream. But maybe I'll feel differently tomorrow. We'll see. So, letting you guys know it may happen. So I just realized this amount of memory bits is fairly high. That's that might indicate the signal tap is actually enabled in this build, so I might want to change that. Might be that it didn't reload the file after I did the stashing stuff. So this might be operating with stale data, because I don't think I'm using nearly this many bits of memory in this particular design, unless signal tap is active, and then I'm using as much as I can to get as many samples as possible. But yeah, updating the software is also probably a good idea. If there's been any maintenance on that controller IP at all, I should be using whatever that is. If it's performance improvements, robustness improvements, timing improvements, I should get on board. But again, other than these kind of issues, like, I'm loving this project. I'm having so much fun designing all this stuff and figuring out like how this, for example, doing this display hardware was actually a lot more fun than I expected. And also iterating on it like this, like now that we got it to work, we can try to simplify it. And I like that iterative approach. It just shows that the workflow is good, that I'm able to throw things together and then change them. But this part of the workflow sucks. Or I'm just waiting on recompiles. Luckily, most of this, when I was developing this, it was almost all in the simulator, because I could kind of go through and, like, the simulations were kind of long in this case because I was generating enough for an entire frame. But then I could kind of go through and make sure that things actually made sense, and it was a lot easier in this setup because, like, if it takes like 3 minutes to compile and get everything on the FPGA, it takes maybe 20 to 30 seconds to just do it in the simulator. So much better workflow. Yeah, I need some crazy server box to speed this up. You're absolutely right. I also need the actual version of Cordis. This is Cordis Lite because it's the free one. And if you shell out like $10,000, you can get the actual one, which I think can compile faster and also has incremental compile features, which is nice. All right, so we'll do this slow path again. Oops. I'll just double click through these menus just to make sure that nothing is stale here. And away we go. Yeah, that'd be nice. I was actually thinking about that. If I make my own simulator for my hardware language, because my hardware language doesn't do multiple clock domains, it doesn't do tri-state logic, or even 4-state logic, as is common in Verilog. And I mean, Verilator doesn't either, as far as I know. So like that should be fine. But like, with those assumptions in mind, okay, look, this works. Okay, this is stupid. Yeah, by the way, this was enabled signal tap. I'm going to disable it and then build it one more time because I have to know. But I think I might do the rest of this off stream. Because it's getting late. So I think I'm going to do that. I'm going to go for now and then try to deal with these issues. And I will see you guys next time. And thanks for hanging out. I forgot to say that. And also the next stream or whenever that's going to be, hopefully I have some basic GPU features. If I stream tomorrow, we'll work on that. Or we'll deal with timing issues. We'll have to find out. But anyway, thanks again, guys, for hanging out. And I'll see you next time.